The idea that we're going to use to do the coloring is called time-forward processing. This is a very powerful idea that is used multiple times in IO algorithms. And here we're going to look at essentially a very simple version of it. The first thing we can observe is that we can identify heads and the tails. Remember that by the previous idea of sorting based on the successor, we could also sort based on the predecessor. So basically, for every element in the list, we can know where its predecessor as well as its successor lies. And based on those two information, we can know whether an element is the head of a list or a tail of the list. And obviously, we know that the heads need to be colored red. And of course, in this case, I'm just looking at the coloring of the forward lists. So we know which element need to be colored red. In this case, it's going to be 3, 4, and 7. Okay. But I do not know I do not know the rest of the elements. And in particular, the main point here is that I cannot just go forward and color the successor of these elements with the opposite color. Because, for example, the successor of 9 is at this position. I cannot go to that element 6 and then just color it, because doing that would require one IO, which I cannot afford. The main idea of time-forward processing is that essentially forward the information in time and retrieve the information when it is the time to essentially access it. Okay? So the main idea here is that we're gonna so let's say assume that the block size is 2. We're gonna read this array 2 by 2, block by block, and somehow magically we will be receiving the colors of the elements in these blocks as we read them. This process of magic receiving color will be done by a priority queue, and I'm going to explain the details now. So we initialize a priority queue, and the initial values in the priority queue will be these heads. So 3, 4, and 7 will be placed in the priority queue with priorities 1, 2, and 6, where these are the positions in the array. Right? So this is position 1, position 2, and position 6. Okay. So priority queue will have essentially 3, 4, and 7. Okay, with priorities 1, 2, and 6. Okay, then in a loop, we repeatedly do this extract min operation from the queue, and then we, I forgot. These are, actually, let me try this again. These are placed with the colors. So 3, 4 are 7 placed with color red in the priority queue, and their priority is 1, 2, and 6. Yeah. We repeatedly do extract min. So here, once we do extract min, we get this element 3, and we know it's a red color. And we know 3 points to element number 5. And therefore we place 5 in the priority queue with priority 3, because it's position 3, and with color blue. So basically we're gonna do this, right? So 5 goes here. The priority is 3, and then 3 will also be deleted, right? Because we have done the extract min operation. And in this case, I'm still reading this block, okay? Because I've processed 3, I'm still processing 4. Then I do extract min, 4 pops up from the array, from the priority queue. I know the neighbor of 4 is 9, it's at position 4, so therefore I place the element 9 with priority 4 into the priority queue. So, okay, I'm running out of space, so 9 here, and the priority is 4. Then we do the extract, we've done the extract min, so it's forgot. Okay. So now my priority queue has 5, 9, and 7 with priorities 3, 4, and 6. And now you can see that when I read the next block, the top of the priority queue is 5. This is because obviously I have processed all the previous elements of the array. So obviously the smallest position that is not being processed is the next block that I'm reading. So naturally 5 will be at top of the priority queue. So I do an extract min on 5, and I get that 5 is a blue element, so it's colored blue. And then I get that the successor of 5 is at position 5. So therefore I insert 8 with priority 5 with color red. I will need some extra space here. So my priority queue is 5, 9, 7, priorities 3, 4, 6. Okay, then I will put 8 with priority 5. So 8 goes here with priority 5. Okay, then I'm done with processing 5 because that's delete min. And then I process the next element. 5 is gone. Next element is 9 with priority 4, and as you can see, magically top of the priority queue because it's the next position that I have not processed. So I do an extract min. I get this element. 9 points to 6. This is at position 5, 6, 7, 8, 9. So position 9. So I put at priority 9. I put the element 6 with color red. Okay, and this process continues. What is interesting here is to notice that the next block I'm processing is going to have 7 and 8. 8 and 7, and 8 and 7 are top of the stack. But when I process 8 and 7, they will insert an element with priority 8 and element with priority 7. So I will get to process those elements next before I get to element 6. So basically, as you can see, this element 6 won't be extracted from the priority queue until I am retrieving this block from the disk. By the time I'm retrieving this block from the disk, all the previous positions have been processed essentially by definition, because the priority queue will have the smallest priority at its top. So therefore, for 6 to be the smallest priority, it requires that all the other previous positions in the array must have been processed. So therefore, whenever I extract 6 from the priority queue, it will be the same time as when I'm reading this block from the disk. And then I will get the color of the element 6, and then essentially I'm done. Well, actually in this case, since 6 is a tail, I will not color it because the assumption is that I have also identified the tails. So basically the algorithm requires a scan of the list as well as n priority queue operations. Scan of the list is O of n over b, and based on the theorem of priority queue, we know that n priority queue operations can be done in sort IOs. So therefore, in total, the list ranking or the coloring can be done in sort time, and with that, we know that the list ranking can be done in sort n time as well.